In this video, we're going to look at the graphs of logarithmic functions. We're going to identify the domain of logarithmic functions, the range of logarithmic functions, and then graph the logarithmic functions. So if you were asked to describe the transformation from the parent function, remember when we have an exponential, if we have an exponential f of x, which is equal to b raised to the x, then g of x would be a b raised to the, let me do this. Let me erase this a minute. Let me make this bigger. Let me put it off to the side. So many things I want to do. Okay, here we go. If f of x is b to the x, and g of x, which is equal to a f of b x minus c plus d is the transformation, then what g would look like would be something like this. A lowercase b, uppercase B, x minus c, and then plus d. Where we know from 1.5 that this and this, the b and the c, are horizontal translations, and the a and the d are vertical translations. So if I come over here, what this does is a horizontal shift. So we're going to shift, horizontal shift, and I'm going to go left 1. So if I have an exponential function that has a base of 2, and this is what it should have looked like, and I would have gone through this point, which is 0, 1, then this moves this left 1, so that point now is -1, not 0. It is -1, comma 1, and it's going to look something like that. So this 100 is a vertical stretch, because it's outside of the function. That's my a, vertical stretch by 100. This -4 would be this b up here, which is a horizontal shrink or compression, terrible, of 1 over the absolute value of -4. So in other words, 1/4. And then the negative is going to reflect it over the y-axis. Okay, so if I were to graph this, it would have normally e to the x would look something like this. This would have been e to the x. And it would have crossed through the point 0, 1. A vertical stretch by 100 means that, put this in a different color, it's going to cross way up here at 100, so it's going to be 0, 100. It is going to be, so that's the stretch. It's going to reflect, so it's going to be decreasing, and it's going to look something like that. Poorly drawn, but something like that. Not drawn to scale, I should say. Okay, and then for this would be the a, and so that's going to reflect over the x-axis. It's going to change the range, and then this is up 1. It's a vertical movement up 1. So here's my original 2 to the x. So 2 to the x should have been right like that. So this is 2 to the x. Would have gone through the point 0, 1. Oh, and it would have had a vertical or horizontal asymptote of y equals 0. Now what happens with a -2, it's going to reflect it down like that, but then it has to move up. So that means my horizontal asymptote is going to move up to y equals 1, and it's going to go through this point, which is 0, 0, and it's going to look something like that. So that is -2 x plus 1. I would recommend that if you didn't have a strong grasp on transformations, now is the time to go back and review and refresh those. So here is some of the things that we are going to talk about characteristic-wise of the logarithmic function graph. First of all, it is one-to-one, and we knew that because it is the inverse of an exponential function. The vertical asymptote, now we didn't have one on the exponential, but we do on the logarithmic, which is x is equal to 0. The domain is from 0 to infinity, so when we talked about this in the last video, we cannot put negative numbers into the log-based b unless, of course, we have a transformation within this log. The range is from negative infinity to infinity. The x-intercept, now we have an x-intercept, is going to be 1, 0. We're going to have a key point at my base value, whether that's e or 10 or 1. Well, actually not 1, but 2 or whatever. It'll be 2, 1. There is no y-intercept without a transformation. It is always increasing if my b value is bigger than 1, and then it's always decreasing if my b value is a fraction between 0 and 1. So here's a decreasing. This is a b that is a fraction, and here is the increase, and here's a b. The base is bigger than 1. So let's talk about what these graphs would look like compared to the original one. So the first thing is we notice that that is a b, which is greater than 1, so it's going to have a shape that looks something like that. And it's also going to go through the point b, 1. Well, if b is 3, it's going to go through, I'm actually just going to graph it over here. I'm going to go 1, 2, so 1, 2, 3. So my b is 3. So it should go through the point 3, 1. But I have a shift here of 4 to the left. So all of my points is going to shift to the left. So my vertical asymptote, which is at x is equal to 0, is going to shift to x is equal to negative 4. My point, which would have been 3, 1, is going to shift to the left. And so it's going to be negative 1, 1. And my range is not going to be affected. My range is still going to be from negative infinity to infinity. My domain did get affected, so it's going to go from negative 4 to infinity, non-inclusive of negative 4. And so if I were to graph this here, it would be right here, negative 1, and it would look something like this. That's what that one would look like if I were to graph it up here. Okay, so now let's take a look at the second one. My b is greater than 1. My b happens to be 5. That tells me my point I should have gone through would have been 5, 1. And then I have some transformations that happen, and my vertical asymptote should have been at x is equal to 0. Now, to be able to talk about the transformations, I have to put it in the appropriate form. So let's sidetrack over here for a moment and say, remember, if I have f of x is equal to the log based b of x, g of x would be capital A f of b x minus c plus d. So g of x would be a, capital A, the log based b. Inside I have a capital B, x minus c plus d. And you can see that this is not in the appropriate form, so I'm going to come over here and fix that. So I'm going to have the log base b. I'm going to factor out a 2. And then I have x plus, and the factor is still going to stay within the log. I'm going to have x plus, and then 9/2 minus 2. Okay, so what does each piece do? Well, we know what this 2 does is going to take all of my x's and divide by 2. So I'm going to do that first, So I'm going to take my x and divide by 2. So now this is going to be 5/2, 1, and this is just going to still be x is equal to 0. Now this part right here takes all my x's and subtracts or goes left. So now I'm going to take my x, I'm going to subtract 9/2. So then this, we know it's going to be 1 there, and this is going to be x is equal to negative 9/2. So I have 5/2 minus 9/2, which is negative 4/2, which is negative 2. So that's where that went to. And then I'm going to take care of this 2 right here, which means I'm going to take all my y's and subtract 2. So it's going to go negative 2 comma negative 1, and doesn't affect my vertical asymptote, which is negative 9/2. So my original graph should have been one that looked like this, and I would have gone through this point right here, because you know all of them would go through the point. I should probably add that extra point of 1, 0. So it should have been 1, 0. So, and then the other one would have been 5, 1. So this other point would have been 5, 1. Let me do the same steps with the point 1, 0. So then the first thing was, it would be, actually I need to back up even more. So let me back up just a little bit more. And so we would have had the 1, 0, then it would have became 1/2, 0. And then here, since I would have subtracted off 9/2, which is negative, it would have turned into negative 4, negative 8 over 2, which is negative 4. So this would have been negative 4, 0. And then my last movement of that would have been negative 4, negative 2. Okay. So the point 0, 1 goes to negative 4, negative 2. So that's where that point, we're going to call this A. This is where A went to. Point B, I'm going to call this B. The point B went to negative 2, negative 1. So it went to negative 2, negative 1. That's where B went to. My horizontal, my vertical asymptote moved to negative 9/2, which is about 4.5. So it went from x is equal to 0 to x is equal to negative 9/2. And bringing this information in, that's about what my graph would look like. Right? So let's take a look at this example. Again, we have to put it in the appropriate form. So we're going to do a negative natural log. We're going to factor out a 3, leaving me x plus 3 minus 7. So remember, if I have an A, I want to put that in the right place. If I would have had an A, a B, a C, and a D, I always do my B's first. So I'm going to start with my ordered pairs, which would have been 1, 0. I would have had E, 1, and my vertical asymptote at x is equal to 0. So I would have taken all of my x's and divided by 3. So I would have had 1 over E, 0. Oh, 1 over 3. 1 over 3, 0. E over 3, 1. And then, of course, we still would have had x equals 0. That wouldn't have done anything for me. Then I would have done x minus 3. That's the second thing I would have done. I would have done my C. So I would have done 1/3 minus 3, which is negative 2 1/3, negative 2 1/3, 0. And then I'm just going to write this as E over 3 minus 3, 1. And then I would have had x is equal to negative 3. So that's where that has moved to. And then I'm going to do my A next. So that is the third thing I'm going to do, which is I'm going to take my y's and multiply by a negative 1. So negative 2 1/3, 0, that didn't change. This is E over 3 minus 3, becomes negative 1, and x is equal to negative 3, does not change. And then my D is the last thing I'm going to do, which is I'm going to take my y's and subtract 7. So negative 2 1/3, and this becomes negative 7. E over 3 minus 3 becomes a negative 8, and it doesn't affect this at all. So I'm going to let you graph that on your graphing calculator or device, but this is where all the points are going to go to. do want to talk about the domain. So the domain was affected by the C value. So my domain here would have been went to -3, infinity. My range doesn't change. It just goes from -infinity to infinity. And up here, my domain would have, because it asked for the domain, would have been -9/2, infinity. And my range would have been from -infinity to infinity. All right, so those are the transformations. Here is an overview of the transformations. That we have the horizontal shifts and the vertical shifts. We have compressions, we have reflections, we have the general equation. I actually added in here, we would have had a cap B here if we have a horizontal compression or stretch. All right, so let's take a look at what each one of these do. So I know that for the original parent function, I would have gone through 1, 0. X is equal to 0 as a vertical asymptote, and I would have gone 3, 1. Now it does ask for 3 points, so I would put in 9 and 2 would come out. This negative and this positive 2 will change the range values. So I first multiply all my y's by a -1, so this would become 1, 0, that did nothing. This does nothing. This becomes 3, -1, and this becomes 9, -2. Then I would have added 2 to all my y's, so this would have been 1, 2. This is still x is equal to 0. This would have been 3, 1, and then this would have been 9, 0. Okay, so my parent function would have gone through 1, 0, 3, 1, and 3, 4, 5, 6, 7, 8, 9, 9, 2. So that's what the original parent function would look like. Now I'm going to go through 1, 2. Still going to go through that point and then this point over here. And oh, that was a terrible drawing. Let's do this. And so that's what the transformed function would look like. And I like to do it point by point. It just makes it easier to do. Okay, so this would go through the point 1, 0. It would go through the point 4, 1. It would go through the point 16, 2, and my vertical asymptote is going to be at 0. So let's put all that information in. Ooh, yeah, you know what? I kind of want to put this more in the middle. Okay. So this is going to affect all of my x's, and it's going to multiply by a negative. So this goes to -1, 0. This goes to -4, 1. This goes to -16, 2. This is still x is equal to 0. This takes all my y's and multiplies by 3, so -1, 0 still. -4, 3. -16, 6, and this still is x is equal to 0. My parent function here is 0, 1, 2, 4, and then the one that's way out here would have looked like this. Here's my parent function. My transformed function would have gone through this one, and then one way out here. And so there is my transformed function. All right, so let's do the last one. The natural log, it was going to go through the points 1, 0, e, 1, e squared, 2, and x is equal to 0. Remember, e is approximately 2.72-ish. We're going to start with this. This is going to take all my x's and subtract 3. So this is going to go -2, 0, e minus 3, 1, e squared minus 3, 2, and x is equal to -3. This is going to take all my y's and multiply by -2. So -2 comma 0, e minus 3 comma -2, e squared minus 3 comma -4, and this is still x is equal to -3. This takes all my y's and subtracts 5, so I'm just going to come over here. -2 comma -5, e minus 3, -7, e squared minus 3, comma -9, and this is still x is equal to -3. And I will let you graph those two. Now, if I'm asked to match the graphs with these logs, remember that if you were to draw their inverses over this line y equals x, this would be 25 to the y is equal to x. That is a pretty big base, so it's going to grow the fastest for an exponential, which means it's going to grow the slowest for the log. So I know that this is e. This would have been 5 to the y is equal to x. This would have been 2 to the y is equal to x. This would have been e to the y is equal to x. And this would have been 10 to the y is equal to x. Now if I start comparing bases, this is the largest, then this one, then this one. E is bigger than 2 because it's 2.72 each. So since y to the 10th is bigger, this must have been D. Y to the 5th is the next one, so that must be C. E to the y must be B. And this last one must be A. And so think about this as exponentials and determine which one as an exponent would have the biggest base. It is the one that's going to grow the fastest. That means in terms of inverses, it's going to be the one that grows the slowest because that's the inverse of fast. So if I had to match my functions with the graphs here, what I would do is look to see what kind of transformations happened. Now this I would rewrite appropriately as the log based 4 of -1 and then x minus 2. The reason I would do that is because now I can see this is a reflection over the x-axis and I'm going to move right to. So reflection over, the y-axis, a reflection over the y-axis and moves 2. So that means this must be b. This one is just a reflection over the x-axis and moving left 2. So reflection over the x-axis and moving left 2 is that one. So that is C. And then all this is a movement left 2. So that has to be A. Now let's determine the graph or the function if the given graph is given to us and the parent function is given to us. Now we know that transformations g of x is equal to a f of b of x minus c plus d. So let's put the parent function here onto the graph. It should go through this point, which is 1, 0. Should go through the point 2, 1, so 2, 1. Should go through the point 4, 2. 4, 2. We have a vertical asymptote at x is equal to 0, and this is what the parent function should look like. Now this graph goes through 0, 0. I can tell that for sure. Just like it goes through -1, 1. And it goes through -3, 2. Now I can see that this horizontal asymptote also has moved. So this is x is equal to 1. So I know inside I'm going to have x minus 1, and that's how I'm going to shift to the left, 1. It looks like it's reflected over the x-axis. So that means that b has to be negative, so I think b is -1. And it doesn't look like I have any movement in the y direction. It doesn't look like I compressed it or stretched it in the vertical direction. It doesn't look like I have any movement up or down in the vertical direction. And so what I think I have is g of x is equal to the log of 2, negative 1, x minus 1, and I think d is 0 and I think a is 1, so I think that's what it is. Now I can check this. The way I check this is if I put in, I don't know what that is, let me erase that, weirdness. So if I put in g of 0, so log base 2 of negative 1, 0 minus 1, which is equal to the log base 2 of 1, this does indeed equal 0. Let's check the other point. G of negative 1, this is the log base 2 of negative 1 minus 1. So this is going to be the log of 2 of 2. So this is 1, so negative 1 went in, 1 came out, so that one checks. Then I have g of negative 3. So this is the log base 2 of negative 1, negative 3 minus 1. So this is the log base 2 of 4, and 2 came out. So yeah, all of my points seem to match. Now there is an algebraic way to do this as well. So if you were to do this algebraically, this is how you would set it up. We assume that d is 0, so we're going to have g of x is equal to a, the log base 2 of b, x minus 1. Now we know that one is for certain. And then we're going to assume that d is 0, so I'm not even going to put d equals 0. So then what I would do is I would do g of 0 is equal to a, the log base 2 of b, 0 minus 1, which is a, the log base 2 of negative b, and I'd set it equal to the output. I would do g of negative 1, which is a, the log base 2 of b of negative 1 minus 1, negative 1 minus 1, which is a, the log base 2 of negative 2b, and I'd set that equal to 1. Then I would do g of negative 3, which is equal to a, the log base 2 of b, negative 3 minus 1, which is equal to a, the log of negative 4b, which is equal to 2. From here, what I would do on each one of these three equations is I would divide both sides by a. So I have the log base 2 of negative b is equal to 0. I would have the log base 2 of negative 2b is equal to 1 over a. And then I would have the log of base 2 of negative 4b is equal to 2 over a. Now the only way this would happen is if b equals negative 1, because 2 to the 0 is 1, and since I can't do a negative log, I can't take the log of a negative number, b would have to be negative 1. So if b equals negative 1, turning this into its equivalent exponential, we're going to have 2 to the 1 over a is equal to negative 2b. So 2 to the 1 over a has to equal positive 2, because if b equals negative 1, that means 1 over a has to equal the exponent here, which is 1. So a also has to equal 1. Similarly, doing this, I'm going to have 2 to the 2 over a is equal to negative 4b, but b is negative 1, so 2 to the 2 over a is equal to positive 4. So 2 over 2a is equal to 2 squared, so 2a is equal to 2, which means a also equals 1. So I can do it algebraically as well. Coming back over to this example here, I am going to do probably the algebraic maybe, But I'm going to start with my parent function. My parent function would have gone through this point, which is 1, 0. It would have gone through 3, 1. And I would have had a vertical asymptote at x is equal to 0. And so this is what the parent function should look like. Now it looks like the point 1, 0 went right here, which looks like it's 3, 0. And I have 3, 3, negative 1, excuse me. This is negative 1, negative 3. I know that point for certain. And my vertical asymptote here has moved to x is equal to negative 4. So when I start building my g of x, which is a f of b x minus c plus d, I know that what I have so far is g of x is equal to a, the log base 3 of b, x plus 4, because that's how it's moved over to the left 4, and then plus d. Now the telling point is the 1, 0 went to negative 1, negative 3. So I have g of negative 3 is equal to a, the log of 3 of b, and I have a negative 4 plus, no, negative 3, excuse me, negative 3 plus 4, negative 3 plus 4. And it looks like I didn't move up, so I'm going to assume that d equals 0. So this becomes a, the log base 3 of b. And this has to equal 0. Divide on both sides by a, the log base 3 of b is equal to 0. 3 to the 0 is equal to b. b has to equal 1. So what I now have is g of x is equal to a, the log base 3 of x plus 4. Now I'm going to check this other point right here. So I'm going to do g of negative 1 is equal to a, the log base 3 of negative 1 plus 4, and it needs to equal negative 3. So I have a, the log base 3 of 3 has to equal negative 3. Divide on both sides by a, the log base 3 of 3 is equal to negative 3 over a. 3 raised to the negative 3 over a has to equal 3. That means negative 3 over a has to equal this exponent, which is 1. That means a has to equal negative 3. So my final answer is g of x is equal to negative 3, the log base 3 of x plus 4. And that satisfies that because we have a vertical stretch of negative 3, a vertical stretch of 3, and it has a reflection over the x-axis. So that makes sense that a is a negative number. And I have a movement horizontally to 4 places, and so that's what I think my graph is. And I believe that's it for this video. We'll see you in class.